Hi everybody, it's Miss Manili, and we are going to begin our unit on inference, and we're going to start by talking about confidence intervals, which are ways that we can estimate a parameter about a population from just a sample. But there are certain things that we have to know in advance. For example, we really have to have a firm understanding of sampling distributions before we can proceed with any kind of formal inference. You have to understand those sampling distributions because everything is based on probability of those distributions. I've also asked that you watch a short video on confidence intervals prior to watching this tutorial, just to give you some background information so you can kind of put all the pieces together. I'm going to apologize in advance. I'm at home on my notebook, which it's a little bit harder for me to write on than it is my smartboard at school, and so my handwriting might not be as neat. My dog is also with me, and so you'll hear her walking around in the background because it's a beautiful day and she's staring at everybody outside and is staring at me and wondering why we're trapped inside. So if you haven't watched the other video already, I'd like you to go ahead and switch back over and watch the Against All Odds video on confidence intervals. All right. So we have several different objectives for today. First, we want to talk about what it is to be a point estimate or a point estimator. We've already been dealing with these. These are just our sample statistics, whether it's X bar, P hat, whether we're looking at a sample standard deviation, variance. The median is even a point estimator. It's basically the value that we're getting from our sample that we're going to be using to estimate the parameter of the population. We're also going to be talking about what it is to be a margin of error. Obviously, we know that all of our sample values are going to vary, but we can kind of estimate what is called a margin of error to give us an actual interval for where we expect the population parameter to fall. So we're going to be able to interpret a confidence interval, interpret a confidence level, and then we're also going to describe how the sample size and the confidence level are going to affect the length of a confidence interval. And then we'll talk about some of the issues like non-response, undercoverage, response bias, and how that can affect the interpretation of our confidence interval. Those are kind of self-explanatory. We've been talking about those problems for a long time. All right, so again, we're just starting our unit on statistical inference, and we know that to infer means to draw conclusions. And we've been doing this all along, making generalizations from a sample value, making generalizations from an experiment. But when we're talking about statistical inference, we're going a little bit further, and we're going to be using probability to describe our confidence, to make decisions even, using what we know about probability. So statistical inference provides us with methods for drawing conclusions from data. We have, of course, like I said, been doing this all along. But what's new with formal inference is that we're going to use probability to express the strength of our conclusions. It's going to allow us to take chance variation into account and to correct our judgment so that we're being very objective and that we can actually make some decisions based on the data that we collect. Even though we don't always, know if the decision is going to be correct, it does enable us to make some conclusions or decisions. So there's basically two types of formal inference procedures in statistics. Something called a confidence interval and something called a test of significance. A confidence interval is what we use when we're trying to estimate a population parameter. So for example, if I wanted to know the mean SAT score of students at Southern High School, certainly I could try to find the value or the SAT scores of every student in Southern High School who's taken the SAT and then find their average, or I could simply take a sample and then based on that sample result, estimate what the population parameter is. And a confidence interval allows us to kind of do that with some certainty. A test of significance is when we want to evaluate a claim about a population. And you guys, have done this informally probably all along. If I made a claim and said, hey, did you know that 70% of guys have their ears pierced? You'd probably be a little bit skeptical of that claim because you're probably thinking about the guys that you know and whether or not they have their ears pierced. And if you know that just a few of your friends who are males have their ears pierced, then that would lead you to suspect that that claim is false. We're just going to take it one step further and do it in a little bit more of an objective fashion. We're going to use what we know about sampling distributions. We're going to be looking at a simple random sample instead of just taking a convenient sample of our friends. And then we're going to look at the likelihood of our sample result to see if we have evidence against the claim. And in our last test, when we were looking at sampling distributions, we actually asked some questions. Do you think that this result shows evidence that, if you remember, like the customs agent, was he being truthful in his claim about the number of passengers that are pulled over for, for baggage checks? Anyway, both types of inference are based on sampling distributions of statistics, and so they report the probabilities of what would happen and if we use the inference method many, many times, if we took many, many samples. So that's why it's really, really important that you do have a firm understanding of those sampling distributions before we proceed. All right, so statistical inference. The methods of formal inference require long-run behavior that probability describes. Inference is going to be most reliable when the data are produced by a properly randomized design. And we talked about this in Unit 2 when we were talking about designing samples and conducting experiments. If you remember, there were two issues when we talked about inference. In order to be able to draw conclusions about a population from a sample, we needed to make sure that the sample was a random sample from that population. We needed to make sure that the sample represented the population. Otherwise, we weren't going to be able to infer. The same was true with experiments. Randomization was the key. If we didn't have a randomized experiment, then we couldn't draw any conclusions about cause and effect. So this just kind of loops back to what we did at the beginning of the year, just to remind you that we want to make sure that our data are objective and that they're representative of the whole population, or that the experiment that we've conducted is properly done, so that we can make those inference decisions, so that we can make those generalizations. If you don't have good data, then there's really no sense wasting your time going any further with inference procedures. You're only going to proceed when the data are worthy of such an analysis. All right, so this is a link to the video that I wanted you to watch from Against All Odds. It doesn't, the sound doesn't work very well when I do it through Smart Notebook, so that's why I want you to look at it separately, please. All right, so confidence intervals, the basics. If you had to give one number to estimate an unknown population parameter, what would it be? Well, if you were trying to estimate the population mean, you're going to probably use X bar, the sample mean. If you wanted to estimate the population proportion, you're going to use the sample proportion. In both cases, you're using what is called a point estimate of the parameter of interest. So a point estimate is just our sample statistic. I don't know why they have to use a different term, but it's essentially our sample statistic. It's the value that we get from our sample value, or from our sample, that we use to make decisions about the population parameter. So a point estimator is just the name of the statistic, whether it's the sample mean, sample proportion. You'll see some examples here. Sample mean, sample proportion, that's our sample standard deviation. Those are point estimators. The actual value that we get from our sample, so like if I said X bar is 15, the 15 would be what I would call my point estimate. We learned in Chapter 7 that the ideal point estimator will have no bias and low variability. So we want to make sure that the center of our sampling distribution is centered around the population parameter, and that we have low variability. We want a spread that is relatively small, and we've learned that by increasing our sample size, we can actually decrease the spread of our sampling distribution. So large samples that are randomized are going to be our goal when we're collecting data. And we know that variability is always going to be present because every sample is going to provide a different result. But we do have some understanding about how that distribution is going to look based on what we did with sampling distributions. Okay, so just to make sure that we understand what it is to be a point estimate or a point estimator, in each of the following settings, you're asked to determine the point estimator that you would use to calculate the value of the point estimate. So in Part A, it says what proportion, P, that would be the population proportion, of U.S. high school students smoke. The 2011 Youth Risk Behavioral Survey questioned a random sample of 15,425 students in grades 9 through 12. Of these, 2,792 said they had smoked cigarettes at least one day in the last month. So if I want to know what the point estimator is, we're trying to figure out what it is that we're calculating. And in this case, we're told that it's the proportion. And so the point estimator, the point estimator in this case then would be the sample proportion, P hat. And the point estimate is going to be whatever the proportion is. So we know that 2,792 out of 15,425. That's all they're asking you to do right now, is just to be able to distinguish between, or to be able to identify what it is that's being measured and then to calculate the value from the sample. So why don't you take a minute to go ahead and do parts B and C, and I'm going to go ahead and I'm going to ask you to press pause until you do. Okay, so I've got all my data in a list right now, and it says basically in letter B that makers of a new golf ball want to estimate the median distance the new balls will travel when hit by a mechanical driver. They select a random sample of 10 balls and measure the distance each ball travels after being hit. The distances in yards are shown below. All right, so we're interested in this problem in the median. So I've entered the data into a list. I'm just going to go ahead to my home screen. I'm just going to use one variable, statistics, with list 1. And in this case, our point estimator is going to be x bar. I'm sorry, no, it's not. I take that back. Delete, delete, delete. We're interested in the median, sorry, so we're going to find the median, and I'm just going to call it a capital M. And if on your calculator you want to scroll down, we find that the median is going to be 285 yards. So our point estimator is the median. Our point estimate is based on this particular sample, and it's 285, and in this case it would be yards. The next one is using the same data. It says, suppose the golf manufacturer is also interested in the variability in the distances traveled and wants to estimate the standard deviation. Well, if I just scroll back up, remember the standard deviation from the sample is S sub x. And so that is going to be 2.271 yards. So our point estimator would be the sample standard deviation, and the point estimate is 2.271, just to make sure you understand the terminology that we're using. All right. So estimating with confidence. Young people have a better chance of full-time employment and good wages if they are good with numbers. Well, how strong are the quantitative skills of young Americans of working age? One source of data is the National Assessment of Educational Progress, and it's the Young Adult Literacy Assessment Survey, which is based on a nationwide probability sample of households. So we're going to kind of start talking about confidence intervals by using an actual example, so that we're learning about it in context, and we're not just talking all about math. All right, so to continue with this example, so the NAEP survey includes a short test of quantitative skills that cover mainly basic arithmetic and the ability to apply it to realistic problems. Scores on the test range from 0 to 500, and we're going to suppose that we know from experience that the standard deviation of scores in the population of all young men is 60. Now, I'm just going to say right now that rarely, I can't even think of a time when you would know the standard deviation of a population without knowing its mean. Because remember, in order to calculate a standard deviation, you have to figure out how far each value is from the mean. So this is an unrealistic situation where we have the standard deviation of the population is given to us. In practice, that's not usually known. So we're just going to kind of start off with this assumption before we move into the more complex formulas that we need when we're starting to look at some more realistic situations and more practical situations. So for now, we're just going to assume that we know the standard deviation of the population. In a recent year, 840 men aged 21 to 25 took the test, and they were part of the sample, and their mean quantitative score was 272. These 840 men, we're going to assume, are a simple random sample from the population of all young men. And on the basis of this sample, what can we say about the true mean of the population of all 9.5 million young men of these ages? So what we're trying to do is estimate the true mean score for young men. So we have a sample of 840, and in the sample, the mean was 272. We also know, again, that the population standard deviation is 60. And again, like, it doesn't make any sense to know the population standard deviation without knowing the population mean. So we're just going to kind of ignore that little hiccup for now, so we can understand how the inference procedures work, and then we'll learn how to deal with that issue in the next couple of chapters. So again, we know that since we took a random sample from the population, that our sample mean should be an unbiased estimator. As long as it's a simple random sample, I know that there shouldn't be any bias in my response. So our mean is an unbiased estimator, and our sample mean is also called the point estimate. Or 272 is known as the point estimate. Well, is the value of the population mean going to be exactly 272? Probably not, because x bar, our sample mean, is 272. We guess that our true mean is somewhere around that value, but we don't really know how close it is, because we know if we were to take another sample, I'm probably going to get a different sample mean. And so what we need to do is go back to thinking about are sampling distributions for X bar. So the first image that you see is the population the population distribution. And we can assume this is a standardized test, so we can see that the population is normal. We do not know the true mean of the population. That's what's unknown. However, we are given that the standard deviation of the population is 60. And again, it really doesn't make any sense to know the standard deviation without the mean, but we're going to ignore that for now. And I know that every time I take a simple random sample of size 840, I'm going to get a different sample result. So the first sample result is shown to be 272, the next one's 270, the next one's 275. But if I were to think about what would happen if I were to hypothetically take, sample after sample after sample of 840 young men, give them this test, and find their average, I know then I have the sampling distribution of X bar, and that's what this distribution looks like. And you'll notice that it's still centered around that unknown population mean. And it should be centered around there because, remember, X bar is an unbiased estimator. So the center of the sampling distribution should match the center of the population, even though we don't know what it is. We also know that because now I'm looking at a sample of 840 men instead of just a sample of one guy, that the spread of my distribution is going to shrink. And so you'll notice that the spread is a little bit smaller, and that makes the peak a little bit higher because the area under both curves, if you remember, has to be 1 or 100%. And the standard deviation for my sampling distribution is just going to be sigma over the square root of n, or in this case, sigma we already knew was 60, and n was 840. And so if I take 60 divided by the square root of 840, I get 207. So now I have the sampling distribution of X bar. I still don't know my population mean, but I do know something about the standard deviation. All right, so the estimate, to estimate the mean NAEP score, we can use our estimate 272 as a point estimate. We don't expect the true mean to be exactly the same as our sample mean, but we do want to kind of talk about how accurate we think it is. We know that in repeated samples, the value of X bar is going to be a normal distribution that has a mean that's unknown and a standard deviation of 2.07. And remember, that's just going to be 60 divided by the square root of 840. The empirical rule tells us that 95% of all of the samples of size 840 are going to be within 2 standard deviations of the mean. And 2 standard deviations, well, if 1 standard deviation is 2.07, then 2 standard deviations is going to be 4.14. So if I think about it, let's look at our normal curve here. My mean is still in the middle, and I know 2 standard deviations from the mean, even though I don't know what the mean is going to be the mean minus 414 and the mean plus 414. And I know that 95% of my samples are going to be in that interval. Well, if the true mean, let me take that back. If 95% of my sample means are going to be within 4.14 points of my true mean, then I can flip it and say that my true mean is going to be within 2 standard deviations of my sample mean, about 95% of my samples. So if X bar is within 4.14 points of mu, then mu is also within 4.14 points of X bar. I know that sounds kind of like a riddle. But basically then what we're saying is the interval from my sample mean minus 2 standard deviations to my sample mean plus 2 standard deviations will capture the true population parameter in about 95% of all samples of size 840. So if I substitute in my sample value of 272, this gives me an interval. And I can basically say that the population mean, even though I don't know what it is, I am 95% confident that it lies between these 2 values, 267.86 and 276.14. And what we've done is we've just calculated the 95% confidence interval for the mean NAEP quantitative score for young men. And so this is the method that we're going to use to calculate confidence intervals. So let's talk about the formula that we use for calculating a confidence interval. So a level C confidence interval, and so we use the letter C to represent our level of confidence. So what we just calculated was a 95% confidence level or confidence interval, but we could also do a 90% confidence interval or a 99% confidence interval. It sort of depends on the situation and how confident you want to be in your estimate. So a level C confidence interval for a parameter is basically an interval that's computed from the sample data by a method that has a probability C, in the last example was 95%, of producing an interval containing the true value of the parameter. Every confidence interval has two parts. It has an interval and a confidence level. The interval always begins with our estimate. So X bar, or our median, or our standard deviation, our sample proportion, it's whatever the estimate is from our sample, plus or minus what we call a margin of error. And the margin of error depends on several things. It depends on our confidence level, it also depends on our standard deviation, which is also going to depend on our sample size. So the margin of error is not always an easy thing to calculate. So we're just going to talk about it in very general terms right now. The difference between the point estimate and the true parameter will be less than the margin of error in C% of all samples. And the confidence level, again, gives the probability that the method produces an interval that covers the parameter. So if we're doing a 95% confidence interval, then I know in 95% of the samples that I calculate, the true mean is going to be contained in 95% of them. Users can choose the confidence level. Most often we do something that's 90% or higher because we do want to be confident. We want to be precise. We want to be sure of our estimate. In the example that we did before, we used a 95% confidence interval. So that would just tell us that our C value is 0.95. That's pretty self-explanatory. So here's another example. So it says 2 weeks before the presidential election, a polling organization asked a random sample of voters the following question. If the presidential election were held today, would you vote for candidate A or candidate B? Based on this poll, the 95% confidence interval for the population proportion, so this time we're dealing with a proportion and not a mean, the confidence interval who favored candidate A, and notice that we're using interval notation here. It's just basically saying that with 95% confidence, we believe that the true population proportion of those that would vote for candidate A is somewhere between 48 and 54%. And that's what it means by interpreting the confidence interval. So I'm gonna give you the actual words because it's really easy to misinterpret the confidence interval. So I'm gonna kind of give you some language that you can use that's correct. Okay, so basically what we mean is we are 95% confident that the true proportion of those who favor candidate A is between 48% and 54%. And that's just a very simple way of interpreting the interval. Notice that we've included our confidence, which is the 95%. We've included the lower and the upper bound, and we're also talking about what it is that we're measuring. In this case, it's the proportion. And the one that was dealing with the test scores, we were dealing with the mean. And again, it's in the context of the problem. So we're 95% confident that the true proportion of those who favor candidate A is somewhere between 48% and 54%. So now it's asking, what is the point estimate that was used to create the interval? So what was my sample proportion in this case? Well, my sample proportion is always going to be in the middle of my interval. And the easiest way to figure that out is to just average the endpoints. So if let me actually just pull up my calculator. So if I simply take an average of the interval, so from 0.48, and add that to 0.54 and divide by 2, it's always right in the middle. So if you take the average, I know that my sample proportion, p hat, is 0.51. Actually, I'm going to just write that because it's going to be hard for me to. So the point estimate in this case, p hat, is 0.51. And then the margin of error is just going to be the difference between the middle and the endpoint. So the difference between 48% and 51%, we're looking at a 3% margin of error. And so we're just going to use the big letters ME for margin of error, and we know that's going to be 0.03. If you want to write in terms of percentages, you can just be consistent. So I know that my sample value from whatever the sample was that I took, the sample proportion was 51%, and my margin of error, which is going to be a combination of several things. It's going to include my confidence level, it's going to include the standard deviation of my sampling distribution, which is going to involve P, it's going to involve my sample size. It's not a straightforward calculation, so we're not going to get into it in much detail yet. So in letter C, it says, based on this interval, a political reporter claims that the majority of registered voters favor candidate A. And then it says to use the interval to comment on his claim. Well, if we think about it, we're 95% confident that the true proportion of those who favor candidate A is somewhere between 48 and 54%. Thing is, that interval includes values that are less than 50%, which means that we can't really say for sure, since the interval contains values that are less than 50%, we really can't be that confident that he's going to win. I don't know, I just know that the true proportion is somewhere in there. So what I would say to respond to this, since the 95% confidence interval contains values less than 50%, we cannot be confident that candidate A will win the election. So this guy is wrong. Now, if the interval went from like 51% to 58%, we'd be 95% confident that the candidate A would win. That would be a different story. But since this interval includes values that are less than 50%, I really can't conclude that he's going to win. I can't be sure he's going to win. Okay, so interpreting confidence levels and confidence intervals. The confidence level is the overall capture rate if the method is used many times. The sample mean we know is going to vary from sample to sample, but when we use the method where we're looking at an estimate plus or minus the margin of error, we get an interval that's based on a sample, and C%, 95%, 90% of these intervals are going to capture the unknown population parameter. So let me show you what I mean. If we take a look, just let me go ahead and pause this for a sec. All right, so if you take a look at this image, you're going to see the distribution of X bars, the sampling distribution of X bars, still with the unknown mean, and you'll see the vertical line in the center that represents that unknown mean. So if you think about what each of these little horizontal lines represents, each one of those red dots is a sample mean. So if you think about doing continuous random samples of the same size over and over and over again, you're going to get a different sample mean for every single sample. And so you're going to see that's what each of those red dots mean. So if we were to construct a confidence interval based on a margin of error that's constant for each of those sample values, then that's what these green arrows represent. That's what that interval represents, is the confidence interval that would be based on the particular sample value. And so there's actually 25 of them, if you notice. And you'll see that in almost all of the intervals that we've collected, notice that almost every single one of them crosses the line where we have our true population parameter mu. All of them but one. And so 1 out of 25, I think, ends up being about 4%. So this is what we mean by a 95% confidence interval. It just means that in 95% of the confidence intervals that I could create from my sampling distribution, in 95% of them, the confidence interval will capture the true mean. And so what we say then is, then I'm 95% confident that the confidence interval that I've found with my sample value is one of the ones that catches the true mean. That's what the interpretation of a confidence interval means. Okay, and so just in terms of like how to write it on your paper, to interpret a C% confidence interval for an unknown parameter, basically we say we are C% confident, and obviously you're going to want to put in 90% or 95% confident that the interval from, and then whatever your endpoints are, captures the actual value of the population parameter. And then you just want to make sure that you're using the context of the problem. So if it's a population proportion or the population mean, you want to just make sure that you use the context of the problem. And then interpreting the confidence level, again, we're just saying, to say that we're 95% confident is basically shorthand for saying if we were to take many samples of the same size from this population, about 95% of them will result in an interval that captures the actual parameter value. And again, that goes back to this image here where we have 25 different sample means, and we've constructed an interval around them. And of the 25 intervals that we created from our sample value, there was only one that didn't actually capture the true mean. And so that's about 4%, which is reasonable if we're doing a 95% confidence interval. Okay, so how do we actually construct a confidence interval? We're going to get into the specifics for each type, because we're going to have formulas that we use when we're dealing with means, and then we're going to have formulas that we use when we're dealing with proportions. So this is just a very broad overview, just a very generic explanation, just so that you get the idea of how to create or construct a confidence interval. So why settle for 95% confidence when estimating a parameter? Well, the price we pay for greater confidence is a wider interval. If I want to be 99% confident, then you can imagine my interval is going to be a lot wider. If I want a narrow interval, then I'm looking at a smaller proportion. So like if I wanted a narrow interval that was only one standard deviation away, I'd have to settle for 68% confidence. So that's the price we pay for selecting a higher level of confidence, because all of our intervals are going to be of the same format, where we have an estimate plus or minus our margin of error. Our estimate comes straight from the sample statistic, and since we're looking at a sampling distribution, we know X bar is normal. About 95% of the values of X bar are going to lie within 2 standard deviations of the unknown mean. So a lot of times, this is essentially what our interval is going to look like if we're talking about a 95% confidence interval, because we know that 95% of our values are going to fall within 2 standard deviations of the mean. Well, if we wanted to be 99.7% confident, then I'm looking now at 3 standard deviations away from my mean, and that's going to make my interval a little bit wider. So the more confident I want to be, the wider my interval is going to be. If I want to have a narrow interval where I'm very specific, I'm going to be less confident that I've captured the true proportion or the true mean. So the parts of our confidence interval look like this. We have our sample statistic, and it's either going to be X bar or P hat. We have what's called a critical value. And the critical value, and actually let me just type it in, it'll be easier. I'll be able to do it a little bit neater. The critical value is based on our confidence level. So for example, if I wanted to be 95% confident, is about 2 standard deviations away. And if I wanted to be, 99.7% confident, then that's going to be like 3 standard deviations away. And if we wanted something in the middle, if I wanted to be like 98% confident or 96% confident, we're actually going to have to go back to our normal distribution and actually find the corresponding Z value. So the critical value is actually going to be what we call a Z star. It's actually going to be a Z with a superscript of a star. We call it a Z star value. And it's based on our level of confidence, essentially, and then whatever distribution we're using. Since we're using a normal curve initially, we'll call it Z, or we'll call it Z star, and that's what we call our critical value. And then we have our standard deviation of the statistic. Well, the standard deviation of the statistic is going to depend on the statistic we're using. If we're dealing with sample proportions, then the standard deviation is going to be the square root of P times 1 minus P over N. If we're dealing with the standard deviation of X bar, then we're dealing with the standard deviation of our population divided by the square root of N. In fact, let me go ahead and just write that down, because I think that'll help you understand it a little bit better. All right, so get my pen. All right, so the standard deviation of the statistic, let me go up here maybe. All right, so if it's for X bar, I know I'm dealing with the standard deviation of the population over the square root of N. And if I'm dealing with the standard deviation of P hat, then I'm dealing with the square root of P times 1 minus P over N. And the statistic, again, is just going to either be X bar or P hat. We're not going to deal with any other statistics. We'll also be looking at the difference between two samples, so we might be looking at the difference between two x bars or the difference between two p hats. And again, like I said, the critical value is going to be dependent upon our confidence level. All right, so the margin of error is just that second part. It is our critical value times the standard deviation of our statistic. The user gets to choose the confidence level, so you can decide if you want to be 68% confident, 75% confident, 95% confident. You decide that ahead of time and then base your interval on that. The critical value is going to depend on the confidence level and, of the sampling distribution, and then the greater confidence obviously is going to require a larger critical value. The standard deviation of the statistic, just like before, is going to depend on our sample size. The larger our sample, the smaller the standard deviation. So let me give you an example. Says to consider a standard normal distribution with a mean 0 and a standard deviation of 1. So that's our standard normal curve. Suppose we want to determine an 80% confidence interval. So first, let's go ahead and sketch this normal density curve. I know that my mean is 0, my standard deviations are 1, 2, and 3 above, and then we've got -1, -2, and -3 below. The empirical rule isn't really helpful with this problem because the empirical rule only gives us exactly 1, 2, or 3 standard deviations away, 68, 95, and 99.7. So if I'm interested in an 80% confidence interval, then I've got to figure out, I know that 80% confidence is going to be a little bit more than 1 standard deviation away, but less than 2. So that's going to be 80%. So if I want to figure out the critical z-values, these points here on my number line, I'm going to need to use the inverse normal operations on my calculator. So if I've got 80% in between, that means I've got 20% on my tails altogether, 10% on this tail, 10% on this tail. So if I use my calculator, and remember with the calculator, if you're going to use the inverse normal function, it's always calculating the area, or it's always using the area to the left. So if I'm going to turn this on and I go to second distributions, we're going to choose our inverse normal operation, and I'm just going to enter in this 0.1. And when I do that, it's going to give me a critical z-value, and that's going to give me this lower bound. So what is it, -1.281? So my handwriting, it's very hard to write on this thing. So my lower value is going to be a -1.281. Well, since this is centered around 0 and we're talking about the central 80%, I'm not going to need to do this again for my upper one. I know my upper one is just going to be a positive 1.282? Let me double check. 1.282, yeah. So the positive and negative z-values, you can simply say that z star, our critical value, is just going to be 1.282. And I know when I'm thinking about my margin of error, I'm going to include a plus or minus. Well, let's go ahead and do that for the most common confidence intervals. Usually the confidence intervals we choose are either going to be 90%, 95, or 99%. So again, think about your, sorry that this is so sloppy, but think about your normal curve. If I want to do a 90% confidence interval, so I've got 90% in the middle. That means I've got 5% here and 5% up here. And so if I use my calculator, I'm just going to use the same command. I'll actually just do second enter. And now I'm going to look for the z-value that's associated with this lower bound. And so I'm just going to type in 0.05. And it gives me a negative 1.645. So I'm going to create a little table here where I'm going to have my 90%, my 95%, and then 99%. And I'd like you to go ahead and press pause and just calculate the z-value. So our critical value for z for 90%, and just keep it positive. It's going to be 1.645. Our confidence interval will take care of the plus or minus. But go ahead and do that for 95 and 99% as well. Okay, so if you've done it correctly for a 95% confidence interval, the critical z-value is going to be 1.96. And for a 99% confidence interval, the critical z-value is going to be 2.576. And we're going to talk about the actual construction of the confidence intervals in the next unit, or in the next section of the unit. But for now, we just wanted to kind of get a general overview of it. So at this point, you should understand what a point estimate is and what the margin of error is. The point estimate, again, is just our sample statistic. The margin of error is going to depend on a couple things. It's going to depend on our level of confidence, our critical value, as well as the standard deviation of our sampling distribution, which is also going to involve our sample size. You should be able to interpret a confidence interval as well as the confidence level. You should also be able to describe how the sample size and the confidence level will affect the confidence interval. A larger sample size is going to give us more confidence. It's going to narrow our interval. It's going to make it smaller. If I increase my confidence level, it's going to increase the width of my interval as well. And then obviously, if we've got issues like non-response, undercoverage, response bias, then we're not really going to want to base our conclusions on any of the data because it's not worthy of any kind of inference. So anyway, I hope that was helpful. If you have any questions, just go ahead and jot them down and we'll take care of it next class.